Hello guys and welcome to Unity Tips video series. In the previous video we looked at some interesting singleton examples and created among others this one with rotating spheres. In this video we will make the spheres respond in a more realistic way to various movements in order to get a more natural experience. Therefore we will utilize some engineering methods that basically anyone without any special knowledge in mathematics and physics can use. In particular, we will talk about an engineering topic called the second order system and integrate it into the existing sphere example. First, what is a system? Basically, a system can be anything that can be described by a mathematical model. So do we need to know math to create systems in Unity? Not really, because you have probably created systems in Unity before without realizing it. For example, when you move an object in the scene, the object movement can be described by a mathematical model. The mathematical model of the system is your object's movement logic that takes some input and returns movement as output. So you have a system. Let's look at the sphere example and how the spheres are moving. We see that the initial position of the sphere is randomly set in the awake method and that the movement happens in the update method. The movement is updated in two steps. First, the new orbit position is calculated based on the given speed and rotation axis. In the second step, the sphere position is set to this new orbit position where the instance position is the center of rotation. The instance is just an empty game object that represents the center. From a system perspective, the output position is updated to the new input position on every update. So we can say that the system output is equal to the input. That's a zero-order system. Run the scene, select the center instance object, and while we move it, the whole structure is moving with it instantaneously. It feels like no physics are involved, as if the spheres are in their own isolated ecosystem and we can only move the system as a whole. That's how a zero-order system works. Very easy to control, very predictable, instant response, and also very artificial feel. Given the intimidating sphere movements, you would not expect to control the system so easily. It doesn't feel natural. Systems where the input and output is sampled at regular time intervals, like this one is updated every frame, is also called a discrete system. The nice thing about discrete systems is that you can very easily mimic higher order systems. The order of the discrete system is determined by the number of previous outputs the system uses to calculate the current output. So to create a first order system, we also need to include the output from the previous update. Given our example, the easiest and most common way to introduce the previous output is to use the vector tree lerp method. This method will interpolate the new position based on the previous position and the desired position by a given factor. The factor may be called damping factor because the first order system introduces damping into the system. You have probably used lerp functions before in the update method and that way created many first order systems without even knowing it. Maybe you've even asked yourself why the time.delta time needs to be used with them in combination. For the discrete system to work properly, we need constant update intervals. Since the update method gets called every frame, it is not guaranteed to be called in equal intervals. The frame rate can fluctuate significantly. The time.delta time holds the fluctuation information and here it is used to steer against and mitigate the fluctuation effect. Run the scene, select the center instance object and while we move it, the sphere smoothly follows the center. The response is not instant anymore but slightly damped. So the first order system can be used for smooth movements, transitions, fading and similar things. Also easy to predict, easy to control and easy to use. Cheap physics. We can tweak the damping factor to get a more natural feel, but it's still not too satisfying. Let's increase the system order. The second order system takes two previous outputs to calculate the current output. In our example, we need a variable to hold the old position which should be used in the following updates. This variable will hold the position from two updates in the past. Now we will modify the calculated position further by combining it with the output from before two updates by a given factor. The factor may be called bounce because the second order system introduces bouncing into the system. It also makes sense to include the bouncing factor into the damping part since bouncing also affects damping. The old position should be set to the initial position in the awake method and also don't forget to store the old position in the update method. The tricky part with second and higher order systems is that you have to be careful when choosing parameters. The system can easily become unstable. There is usually a sweet spot range where the system is stable and the easiest way to find it is by testing. I've chosen 12 for damping and 0.9 for bouncing. Run the scene and first you will notice a wiggle at the scene start. That's the effect of a not stable update interval. Once the FPS or frames per second stabilizes, the system also stabilizes. It's very sensitive to update interval fluctuations. The recommendation here is to use the fixed update method instead of the regular update method. Fixed update can still vary, but in our case it isn't noticeable. With a stable update interval, the system stability now depends only on the chosen parameters. Run the scene. This is a stable system. If I change the bounce to 1.1, which is outside of the stable range, and start the scene, this is an unstable system. It will never settle into a stable state. Changing bounce back to 0.9, and let's look again at how it behaves. Select the center instance object, and while we move it, the sphere smoothly follows the center and also bounces into place when we stop moving. Bouncing and settling into place is a characteristic of a second order system. Response in general is a bit faster than in first order systems, and it can be controlled with the right set of parameters. How does it feel? Definitely more fun to play with, but for this sphere structure I would not expect to behave so solid. Like the individual spheres are not affected by the movements, only the whole structure is affected. Should we again increase the order of the system? Actually, going beyond the second order would not introduce any noticeable differences. The second order system is sufficient for most applications. We can, for example, introduce some distortion into the sphere orbits. The distortion amount can be controlled by the difference from the actual radius caused by our movements. The faster we move the spheres, the greater the difference from the actual orbit radius. The arrow can be then used as an interpolation driver between the initial orbit position and the new displaced orbit position. I will introduce another factor here called pull, because the displacement will be manifested as pull. Start the scene and select the center instance object. As we move it, the spheres are getting squeezed together as if they were pulled by some force and then bounce into place when we stop moving. It doesn't feel so solid anymore, it's more like jelly, like the individual spheres are really influenced by the movement. There is one more trick we can use to make this feel even more fluid. We can introduce an additional error by spinning the previous position around the moved center. If we don't move the center, the error will be very small, but the faster we move the center, the more noticeable it will become. Start the scene. Feels very elastic, and even the shape can be altered temporarily. It's maybe a bit too bouncy for my taste, but definitely a step in the right direction. We can still tweak the parameters to get the right feel. I will decrease the bounce to 0.8 and increase the pull to 1. Start the scene. This is more how I would expect it to behave. Feels right to me. Now some final thoughts. Is this now still a second order system? For the most part it is, but with the introduction of errors it became a non-linear system. For us it doesn't actually matter if it's linear or not, as long as it is stable and as long as it has the properties of a second order system such as damping and bouncing. The theory behind systems is complex and math intensive, but simulating discrete systems like this one in Unity is very easy and actually quite useful for simulating physics that you would otherwise not be able to achieve. Thank you very much for watching. I hope you now have a better understanding of how systems work and how to use them in Unity. If you found this video interesting and want to see more videos like this one, give a like, subscribe and hit the bell icon to get notified when I release new videos. Also feel free to comment. See you in the next one. Bye.